Welcome back. Today we're going to be talking about precedence rules, or in other words, the order of operations for these logical operators. So as an analogy to set up, I'd like you to recall PEMDAS, which you all know from the order of operations of our basic arithmetic. So in that goes parentheses, exponents, multiplication, division, addition, subtraction. And you know that parentheses is number one, and then it goes on down the list. Multiplication and division are on the same hierarchy, and so the only way to distinguish between those are left to right. And same with addition and subtraction, those are in the same hierarchy and go left to right. So the logical operators have a similar sort of priority queue. I'll list them out here. So first goes negation, then goes the AND operator, or the conjunction, then the exclusive OR, then OR, inclusively, then implication, so I'll say conditional, and then biconditional. Important to note is that the negation is number one. So that one's always going to take precedence over all others. And then it does follow a pretty strict, then goes and, XOR, or conditional, biconditional. And if at the very end, we'll follow left to right. So for example, A or B and C. Going through these one at a time, we for sure have negation that's going to go first. So I like to just kind of say, okay, there's my negation. So I'm going to rewrite that, and I'm going to use these triple lines that's logically equivalent to A or negation B and C. And then next up, I have to look for, are there any ands, right? Because that's number two here. And it's true, we have a and right here. So I'm going to group these together now. And I'll continue this way so it's all in one line. Then A or not B and C. And then that would be it really. At that point, we know that we're going to start here and then work our way out to the parentheses and then finally finish off with A or whatever comes out of that parentheses. In either way, I like to put parentheses just like I would if I was doing a really complicated math expression like 3 plus 2 times 5 divided by 10. Right, I'd want to put the parentheses first. Right, this is kind of messy. You see those in those social media posts where it's like, you don't know how to do math. It's really silly. Just follow parentheses. I don't know why anyone would want to write it any other way. Okay, so that's your example with how to use the order of operations. Let's go through one more example in your book that I think is a little unclear. I think it's the question or reading exercise or reading question 2.41. So question 2.41. And the asks are A intersect B or C logically equivalent, or sorry, I should say, is A and B, parentheses, or C logically equivalent to A intersect B or C. So that's our setup. In the next section, 2.2, we're going to talk about truth tables some more, and we talked about them in a previous video, so check that out. But truth tables is one way to go about it, and you should also try to think of it in different ways, because truth tables you could do, but since there's three variables, right, A, B, and C, A, B, and C, we're going to have to write 8 rows in our truth table. And it's not all that difficult or time consuming, and I encourage you to do it, but we'll try to think about it a different way. So the way I see this is that we really have kind of one statement here connected with the or C. And then on the other hand, for this statement here, I see A by itself and another color in here, another by itself. So it's really, we're kind of checking an or statement versus an and statement. And ors and ands are fundamentally different, meaning ors can be true as long as one of these blue piece or C is true. On the other hand, this A statement over here, this A statement is only going to be true if both that pink A piece and the green piece are true. So that's kind of the strategy. So on this side, I'll say the left-hand side, I'm going to say, well, let's set T to be true. So I'm going to say C's is true. Then blue can be anything. So A and B can be anything. And in fact, I'm going to say, well, let's make A and B false. Then we have this like false and false. And then that blue all together, false and false makes false, but false or true makes true. So with these three variables or propositions set up as false, false, and true, A, B, C, on the left-hand side, I get true. On the right-hand side now, because, like I said, A in the beginning is really going to command a lot of this power in this and statement, and I said A is false, then I have a false, and, well, it really doesn't matter what comes out of this green now, because no matter what, false and something else is going to be false overall. And we can double check it with the statements we have. So we have B is false, C is true. So we said false or true. And false or true is true. So it turns out we get a true out of that green. But because we have a false and true here, the overall is going to be false. So you see that our first statement, A and B or C, with the parentheses on A and B, is not logically equivalent to A and parentheses B or C. So no, these two propositional statements are not logically equivalent. And the reason being is that we were able to find variables A, B, and C that didn't hold true. And you want to think of it the same way as you would think about it with some algebra. So when I say these two propositional statements are not logically equivalent because we found values for A, B, C that didn't satisfy the identity is, I'm really trying to say, okay, are these two, the one in yellow and the one in green, are they logically equivalent? Is this some identity, kind of like an algebraic identity? And it's not true because we found values for those three variables such that they wouldn't equal the same truth value. And the analogy here goes back to some algebra. So for example, someone said, is this algebra identity true? Let's say x plus y squared equals x squared plus y squared. One of the most common algebraic mistakes that middle and high schoolers are going to make. They think this squared is just going to distribute across. And no, this is not true. And here's like your example. I'm going to find variables x and y that make this identity not compatible or not equal to each other. So for example, x equals -1 and y equals 1. Then on the left-hand side, I have -1 plus 1 squared. That's 0 squared, and that's 0. On the other hand, on this right-hand side, I'm going to have -1 squared plus 1 squared. That's 1 plus 1, and that's 2. And 2 does not equal 0. Okay, so this is just the analogy I want you to think in your mind is this identity true? Are these two algebraic statements true? No, they're not true because I found x and y that showed that they're not always equal. And that's the same way we showed that these are not logically equivalent. We found some values a, b, and c. They're not numbers anymore, they're truth values, such that when I kind of went through the motions on the left-hand side with the yellow, it came out to be true overall. And on the right-hand side, went through the motions, it went out to be false overall. So they're not the equal truth value like you'd like. So go back and forth, and you'll see that the analogies between this algebra are very similar to the analogies of this logical statement. In the next section, we're going to talk more about using truth tables to prove some things are logically equivalent or not, and I'll see you in the next video.